In this video, we're going to track through the complete solution of a fairly long problem, a non-standard problem. The problem involves a character named Vern who is planning a vegetarian diet. Now, in the setup of this problem, we're going to continually need to refer back to the problem description that's shown here. So you might want to open the PDF file that corresponds to this movie so that you can keep this slide open for reference while we're navigating our way through this movie. Vern is adopting a vegetarian diet consisting of fruit, grains, and vegetables, and the bottom line decision he has to make is how many servings of each type food to eat per day in order to satisfy his daily food requirements at minimum costs. So we'll have three variables corresponding to how many ounces of each of the three foods, fruits, grains, and vegetables he eats. We have minimum daily requirements for protein, for carbohydrates, for fiber. We have data on what's contained in a serving of fruit in terms of those three nutrients. We have information about what's contained in grains and what's contained in vegetables. So we know about the three foods. We know the cost information. Fruit costs 30 cents per serving, grains 60 cents, vegetables 70 cents. And the bottom line is, as I indicated, how much of each type food should he eat in order to minimize the cost of the diet, and what would the cost be. So we begin with X being the number of servings of fruit, Y the number of servings of grain, and Z the number of servings of veggies. The constraints given verbally in the problem translate into a protein constraint inequality, a carbohydrate constraint, and a fiber constraint. And as usual, we have our non-negative constraints. The protein constraint, for example, comes from the fact that the amount of protein obtained from fruits plus the amount of protein from grains plus the amount of protein from vegetables has to be at least the minimum daily requirement for protein, and similarly for carbs and for fiber. We're minimizing the cost, which is 30 cents per serving for fruit, 60 cents per serving for grain, and 70 cents per serving for veggies. So there's our cost function. So this problem is non-standard in just about every respect. All the three constraints here are greater than or equal to constraints, and it's a minimization problem. So we have to take all three of the constraints, multiply them by -1, so that they're less than or equal type constraints. And we will be maximizing D, which is the negative of the cost. So when we introduce our slack variables into these inequalities, we have slack variables U, V, and W as shown here, and our equation for D, when put into standard form, is as shown. So these are the four equations that provide the input for our initial simplex tableau. The tableau has an X column, a Y column, and Z column for our original three variables. U, V, and W columns corresponding to the three slack variables, a D column, and the numbers on the right sides of the equation. So this is what we're starting with. We have no negative numbers in the bottom row. We have a choice of three negative numbers to look at for starters in that column. No matter which of these negative numbers we focus on, we find negative numbers to the left in all of the first three columns. So no matter which of these we look at for starters, we're going to wind up with a choice of columns 1, 2, or 3 as the column where our pivot element comes from. If we look at the -14, we see the negatives in those three columns, which indicates a choice of those three columns. And similarly, if we look at the -16 or the -12. If we were to choose the first column as our first pivot column. We would of course be comparing the ratios -1 into -14, which is 14. -2 into -16 would give us an 8. And -1 into -12 would give us a 12. So the smallest ratio, if we're working in the first column, would be obtained by dividing -2 into -16. So if we're in the first column, our pivot element has to be -2. If you check ratios in the second column, you would find that in the second column, the pivot element would need to be -3. If we decided to work in the third column, we would find, checking those ratios, that our pivot element would have to be -4 if we were choosing from the third column. So in any case, these would be our three choices for the first pivot element, depending on which column we decided to pick it from. Let's go with the -2 in the first column and see where that takes us. We would do -1/2 times row 2 to make that into a 1. And then we would do row 1 plus row 2, row 3 plus row 2, row 4 minus 30 row 2 to make the other guys into zeros. And that would take us to the simplex tableau shown here. We know we're still not in the solution region because we have this -6 and -4 sitting over in the final column above the bottom spot. So for our next pivot element, we have a choice of focusing on the -6, which says, looking to the left where we have negatives in these three spots, we can choose either the Y, Z, or V columns as our next pivot column. If we look at the -4, we see we have exactly the same three choices. Y, Z, and V columns are the columns where we have a negative to the left of the -4. So bottom line, our next pivot column has to be either the Y column, the Z column, or the V column. We don't really have much basis for choosing one over the other. We might want to make our choice just depending on which numbers look easier to work with. Here I've tested the ratios to see what the three possible pivot elements would be. If we choose the second column, the pivot element would have to be -2, and that's because it would give us a ratio of 2. This ratio would be 8. This ratio would be 3, so the smallest ratio is obtained with the -2. So if we're working in column 2, the pivot element has to be the -2. You can check for yourself and find out if you're working in column 3, the pivot element would have to be -5/2, or in the V column it would have to be -1/2. So we could pick any of those three choices for our next pivot element. Let's pick the -1/2 in the V column and see what happens. We would multiply through by -2 to make that into a 1. Multiply row 3 times -2. And at that stage the V column is this. And here in fact I've also shown the additional steps that would be required to make the other numbers in that column equal to 0. So I'm actually showing you here the result of the entire next step, making that pivot element a 1 and the other numbers a 0. Here's where we are after the complete step. And at this point, notice that we still have a negative in the far right over here, so we're still not in the solution region. If you wanted to talk about the spot in three-dimensional space where we are located, it's where x is 12, y is 0 because its column is not in the basic form, and similarly for z. But in any case, we're not yet in the solution region, so we have to repeat the process. Look at this -2. We have negatives in this spot and in this spot, which means we have a choice of the Z column or the W column as being the column from which our next pivot element comes. Let's just arbitrarily pick the W column, and the red circle shows that the pivot element would be the -1. Let's check and make sure that's correct. -1 into -2 is 2. -1 into 12 is, that's a negative number, so we can't possibly have that one. And similarly, this gives us a negative number. So in fact, the -1 is the only choice in that column that even gives us a positive ratio, so it wins automatically. -1 is the next pivot element. We want to make that into a 1 and the other numbers in that column into zeros. After that's done, this is what we're looking at. So here's where we land after the next step. And finally, we're rid of the negatives over here, which means we have finally made our way into the solution region. Interpreting where we are, the y column is not in basic form, so y is 0. The z column is not in basic form, so z is 0. The x column is, so if we block out the y column, the z column, and the u column, which are the ones not in basic form, the second row would say x is equal to 14. So we would be looking at a diet consisting of 14 servings of, what was the first variable? Was it fruit? 14 servings of fruit, no servings of grains, no servings of veggies, which would be a pretty dull diet, wouldn't it? The associated value of D would be minus 420. So the associated value of C would be plus 420. But we don't need to worry about this too much because we're not yet at the optimal solution. We still have negative numbers in this bottom row. So since we have cleared out all the negatives over here, we now look at these negative numbers in the bottom row, pick the most negative, which is minus 50, and proceed along just as we do with standard problems. 5 into 12, 4 into 14, or 2 into 2 actually gives the smallest ratio. So 2 is going to be the next pivot element. We turn the 2 into a 1, and the other numbers in the z column get turned into zeros, and that will bring us to the tableau that's shown here. Notice we're still in the solution region. There are no negative numbers over here, but we're still not at the optimal corner point because we have this negative number in the bottom row. What we're looking at in this scenario is a diet that would consist of 10 servings of fruit, no grains, 1 serving of veggies. It would be lower cost than the last diet, but still not optimal, as the minus 30 tells us. So we have to work with the y column, find yet another pivot element. 4 into 7 is smaller than 3 into 10. 0 can't be the pivot element. So the 4 is going to be our next pivot element. We pivot on the 4, turning it into a 1, and the other numbers in that column into zeros, and we arrive at the tableau that's shown here. And finally, we're done. We have no negative numbers in the far column, so we're still in the solution region, and we have no negatives down here in the bottom row, which means we are at the optimal solution. What is it? The U column, the V column, and the W column are all not in basic form, so they all get set equal to 0. The first row says Z is 1. The second row says X is 19/4, which is 4 3/4. And the third row says Y is 7/4, which is 1 3/4. And the D value, minus 635 over 2, is minus 317.5. So that's talking about a diet of what? 4 3/4 servings of fruit, 1 3/4 servings of grain, 1 serving of vegetables. D is minus 17.5, so the minimum value of C would be plus 17.5. That is, the minimum cost is minus $3.17.5, and it's obtained by eating 4 3/4 servings of fruit, 1 3/4 servings of grain, 1 servings of vegetables. So there's our summary of what we've done after I've lost track of how many steps it took, but we eventually got there. For a while we were not in the solution region, then we got into the solution region, and by doing additional steps arrived at the optimal corner point. One simple final example to illustrate one particular point. Suppose you were doing this very simple looking problem. Maximize p equals 2x plus y, subject to these unusual looking constraints. They're unusual because we have these negative numbers here, which is not common. This is a standard problem. We're maximizing, and we have less than or equal constraints, and we have non-negative numbers on the right. So this is a standard problem, but I'm going to tack it onto this video because it illustrates something we've never seen before. You add the slack variables u and v, and that gives us these two equations and the profit equation, which go into the initial simplex tableau. So the initial tableau is as shown here. The x column, the y column, the columns for the two slack variables, the column for p, and the numbers on the right. Now, what's interesting about this problem is when you go to pick a pivot element. The most negative number in the bottom row is -2. So the pivot element needs to come from column 1. We have a choice 1 into 1 or -1 into 1 gives us a negative number, so that's not going to be the pivot element. 1 is the only choice for pivot element. The 1 is already a 1, of course, so we don't need to do anything to that first row, but we need to make the other two entries in that column into 0. So we need to do row 2 plus row 1 and row 3 plus 2 times row 1. When you do those two row operations, this is what you arrive at. We're not at an optimal solution because we still have this negative number in the bottom row, but look at our problem. We don't have any way of picking a pivot element because in that second column where the -3 is, -1 can't be the pivot element. That doesn't even give us a positive ratio, -1 into 1, and 0 can never be a pivot element. So we're stuck in this paradoxical situation where we haven't found the optimal solution, but yet we can't choose a pivot element. So what's the simplex method trying to tell us in this scenario? Basically, what it's telling us is that there is no solution to this problem, that the nature of the solution region is such that there is no maximum value for the function p in the solution region. Now that may seem paradoxical to you, but it's true. If you were to draw a picture, if you were to try to do this problem graphically, and you were to draw a picture and see what the solution region looks like, what you would find is that the solution region extends indefinitely far out into the first quadrant, and that the further out you proceed away from the origin, the larger and larger the profit gets, and there is no way to maximize the profit because there's no limit in how far out in the solution region you can travel, but there aren't any corner points out there which would serve to maximize it. So the information it's giving us is true, but the way it tells us that is through the inability to find a legitimate pivot element.